Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Physically confined spaces can make for more efficient chemical reactions, according to recent studies led by scientists from the U.S. Department of Energy's Brookhaven National Laboratory. They found that partially covering metal surfaces acting as catalysts, or materials that speed up reactions, with thin films of silica can impact the energies and rates of these reactions. The thin silica forms a two-dimensional (2D) array of hexagonal prism-shaped cages containing silicon and oxygen atoms. These porous silica frameworks are the thickness of only 3 atoms, explained Samuel Tenney, a chemist in the Interface Science and Catalysis group of Brookhaven Lab's Center for Functional Nanomaterials (CFN). If the pores were too tall, certain branches of molecules wouldn't be able to reach the interface. There's a particular geometry in which molecules can come in and bind, sort of like the way an enzyme and a substrate lock together. Molecules with the appropriate size can slip through the pores and interact with the catalytically active metal surface. The bilayer silica is not actually anchored to the metal surface, added Callie Eads, a research associate in the same group. There are weak forces in between. This weak interaction allows molecules not only to penetrate the pores but also to explore the catalytic surface and find the most reactive sites and optimized reaction geometry by moving horizontally in the confined space in between the bilayer and metal. If it was anchored, the bilayer would only have one pore site for each molecule to interact with the metal. The scientists are discovering that the confined spaces modify different types of reactions, and they are working to understand why. Tenney and Eads are co-corresponding authors on recently published research in Invention Chemistry demonstrating this confinement effect for an industrially important reaction, carbon monoxide oxidation. Carbon monoxide is a toxic component of engine exhaust from vehicles and thus must be removed. With the help of an appropriate precious metal catalyst such as palladium, platinum, or rhodium, catalytic converters in vehicles combine carbon monoxide with oxygen to form carbon dioxide. Tenney, Eads, and colleagues at the CFN and Brookhaven's National Synchrotron Light Source 2 (NSLS2) showed that covering palladium with silica boosts the amount of carbon dioxide produced by 20%, as compared to the reaction on bare palladium. To achieve this performance enhancement, the scientists first had to get a full bilayer structure across the palladium surface. To do so, they heated a calibrated amount of silicon to sublimation temperatures in a high-pressure oxygen environment. In sublimation, a solid directly transforms into a gas. As the thin film of silica was being created, they probed its structure with low-energy electron diffraction. In this technique, electrons striking a material diffract in a pattern characteristic of the material's crystalline structure. We continue heating until we get highly crystalline structures with well-defined pore sizes that we can use to explore the chemistry we're interested in, said Eads. Here, the team tracked reactants and products and the chemical bonding environment in a 2D confined space during oxidation of carbon monoxide, incrementally increasing the temperature. To track this information, they simultaneously conducted ambient pressure X-ray photoelectron spectroscopy (APXPS) and mass spectrometry (MS) at the NSLS2 and infrared reflection absorption spectroscopy (IRAAS) at the CFN. APXPS tells us what elements are present, whether they're on the surface or in the gas phase, said Tenney. It can also give us information about the chemical oxidation state or binding geometry of the atoms, whether a carbon is bound to one or two oxygen atoms, for example. MS helps us identify the gas phase molecules we're seeing evolve in our system on the basis of their weight and charge. IRRAS is a fingerprint of the type of chemical bonds present between atoms and shows the conformation and orientation of carbon monoxide molecules adsorbed on the surface. According to co-author Dario Stacchiola, leader of the CFN Interface Science and Catalysis Group, one of the team's unique capabilities is the ability to use complementary surface characterization tools to analyze the same sample without exposing it to air, which could cause contamination. Reproducibility is often a problem in catalysis, said Stacchiola, but we have a setup that allows us to prepare a sample in very pristine ultra-high vacuum conditions and expose the same sample to industrially relevant pressures of gases. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.